creating 3D models for marine and coastal monitoring and outreach is a very hot subject. Myself, as a marine ecologist, I got introduced to it in recent years. And of course, as you will also see through the presentation, it has been becoming even more and more advanced and important for various disciplines. Nikhil, can you go to the next slide? I'll quickly introduce PUREEF-Y project. The full title is Past, Present, and Future Status and Mitigation for Cyprus Shallow Water Reef Biodiversity and Functioning Under Global Change. This is a project funded under Horizon Wydera. It's a twinning project. It started in June 2024, so we're already 1 year into the project, and it lasts for 36 months. CMMI is the coordinator, but we also have advanced partners from the Autonomous University of Barcelona, but also from the IOLR, the Israeli Oceanographic and Limnological Research Center. Very quickly, the main objectives of the project are capacity building in the areas of chemical oceanography, marine ecology, but also innovation management and policy making. It involves quite a lot of networking activities, such as conferences, summer schools, seminars, and webinars, such as the one that we are of course, there's a lot of dissemination, communication, and outreach, but the research and innovation component of the project, the scientific part, focuses, as the title suggests, on understanding, assessing the paleo, so the past, and the current physical-chemical parameters, including pollutants of important habitats with respect to shallow reefs. Marine biota, understanding the marine biota status of these reefs around Cyprus. We try to investigate at the same time the effects of stressors such as climate change and pollution on key species. I have some images in this slide, as you can see on the right side, of some of the selected organisms, important organisms such as bioconstructions of the Mediterranean vermedid gastropod vermedus reefs. These are biogenic engineers, some of the main biogenic engineers in the region. They have many positive effects. They protect coasts from erosion. They serve as carbon sinks. They provide habitat for many organisms. So these are some of the main organisms that we're focusing our research on, but also other associated organisms such as Cystoceira forests and urchins, which Cystoceira are the most common macrophytes in these shallow sublittoral habitats in the Med, and they also play a key role in supporting biodiversity, food webs, and carbon sequestration. So this is in a nutshell PUREEF-Y. Now, next slide, please, Nikhil. I'd like to introduce first our moderator, Professor Gil Rilov. He's also the coordinator in PUREEF-Y, the manager in PUREEF-Y from the Israeli partners, the IOLR. He's a senior researcher at the National Institute of Oceanography at the IOLR, and he's also a professor at the University of Haifa. He heads the Marine Community Ecology Lab at IOLR that studies coastal ecological communities related to the project, of course, and the impacts of global climate change and bioinnovations and local fishing pollution, these stressors and their combinations on coastal biodiversity, ecological functions, services, and conservation approaches. Over the years, he has worked on different coasts, from the Red Sea to the Mediterranean Sea, even to the coast around New Zealand, the east and west coast of the USA, and the shores of the Northeast Atlantic. And he uses experimental approaches such as mesocosms and in situ experiments to understand the tropicalization process and its current and future impacts on the Levantine reef communities and their functioning. Currently, he's on sabbatical leave as a visiting professor at CESM, the Mediterranean Science Commission based on Monaco. He will be moderating the questions and answers session at the end of the presentation. And now I'd like to present, to introduce you to the main speaker, Mr. Nikhil Thomas. He is a marine biologist specializing in the application of underwater photogrammetry in marine ecosystem monitoring. He received his master's degree from a joint master's program entitled International Masters of Science in Marine Biological Resources, which was hosted by 11 leading European institutions. He was awarded the prestigious Erasmus Plus scholarship for the particular program, and he has previously collaborated with NGOs, government institutions, private companies, and independent researchers across India. He comes from India on a wide range of topics related to marine restoration and conservation. So he has joined CMMI more than a year ago in 2024, and he has been actively involved in various projects that harness the power of photogrammetry for both scientific research and raising public awareness. Nikhil, the floor is yours.
Thank you, Louis. Thank you so much. Thank you all for joining the webinar. It's a great pleasure to be presenting about structure from motion photogrammetry for you guys. I came across photogrammetry a couple of years ago myself. It was very coincidental. I was looking for a thesis topic very deliberately. That's when my then supervisor, now friend, mentioned about photogrammetry in one of his classes. And that's when I thought to myself, this is the best combination. I get to dive, I get to do photography, two of the favorite things I like, and it could be used for marine science. Since then, I've been pretty much trying to learn more and more about photogrammetry, and I've tried to compile the things and techniques I've learned over the years for this webinar today. I really hope you can get some key takeaways and you'll try the technology or application yourselves as well at a later stage. So I structured the presentation in the following way. First, we start with a brief history and introduction of what photogrammetry is and what structure from motion photogrammetry is. Then we'll move on to why photogrammetry and if there are any applications that you could incorporate in your projects. And then we'll move on to the data formats and methodology to achieve the results for structure from motion photogrammetry. And then we'd see how these outputs of photogrammetry could be used for communication and dissemination. And lastly, the limitations. This is purely a webinar where we're going to talk about photogrammetry in marine setting and not terrestrial setting. So let's get started. So first of all, what is photogrammetry? In the most simplest term, if any, it's a technique where measurements are derived from a pair of images. It's as simple as it gets. And it's derived from the Greek terms phos, grapho, and metron. I'm sure that my colleagues here who speak Greek can confirm this, which means light, to write, or to draw, and to measure. So how does it come into picture? In the early 1850s, there was this French engineer who first, based on ground photograph, derived some measurements. That's how photogrammetry, traditional photogrammetry, came into picture. Later, in the 1900s, they were using balloons, kites, and planes to have aerial photogrammetry. However, it wasn't very accessible to the common people. And in the years, with technological advancements in terms of our first underwater camera, first underwater flash, advancement in sensors, advancements in the computing powers, advancements in algorithms like SIF, bundle adjustments, all of these resulted in the modern day structure from motion photogrammetry. You'd be wondering what structure from motion photogrammetry means. Why structure from motion? So If you see this picture here with the coral, I don't know if you're able to see the mouse, but the boxes in here, the blue boxes or squares in here, is basically representation of camera. So when you say subject from motion, the subject here is the coral, for which we are trying to estimate the geometry or the matrices, and it's derived using a particular motion. That's how the name structure from motion comes into picture. In the very recent years, since the last 2 years maybe, this technique has an extension to something that we call 3D Gaussian splatting. This is a space that's fast evolving on a daily basis. It's hard to literally catch up on the amount of research that's happening. How does this come into picture? So it tackles two of the main downfalls of photogrammetry. That is, it's better tolerance to reflective and transparent surfaces. However, and it doesn't need a lot of memory in terms of storage and computing. You can run it on a very normal PC. However, in comparison to structure from motion photogrammetry, it still lacks geometric accuracy. So if it's for scientific purposes, it's not a recommended tool yet. Hopefully in the future, we would have some way to use it as well. And now, if you look here, in the year 2015, there's something incredible happening. This is a graph. If you notice here, since 2015, there has been an increase in the number of publications using structure from motion photogrammetry. And this is across various fields like archaeology, biology, ecology, engineering, and so on. And the same is happening in marine sciences, especially ecology. So 2015 was like a peak of publications, or scientific community started recognizing this as an important tool. So you'd be wondering, so why exactly structure from motion photogrammetry, or how can I use this in my research? First of all, it's non-destructive. If you see the coral here, it's like a 3D model of a coral, and this is like the camera pattern that's used to create this 3D model. Traditionally, if you had to get morphometrics, let's say surface area or volume of a coral or any object from underwater, a sponge, for example, you'd have to probably take it out of the water, and it's a very destructive methodology where potentially the organism wouldn't survive. If it's not an organism scale, if you wanted to measure the structural complexity of a reef, you'd use traditionally something called as a chain and tape method, where a long chain is laid onto the reef to then estimate the structural complexity. However, in this case here, all of this is done virtually using structure from motion photogrammetry outputs. So just from basic photographs, without disturbing any organism or habitat, you can estimate morphometrics like surface area, volume, and more with higher accuracies. The second thing, it can take measurements from a colony scale. You can use it from a colony scale to a whole habitat or ecosystem scale like you see here. And the best part, it could be applicable from the intertidal area to even the deep seas. If you see here, photogrammetry covers a big range of scale and resolution. So that's one of the greatest advantages as well. Coming to accuracy. For us scientists, accuracy in terms of surface area or cover, numbers are very important. Don't get too confused with the research happening in here. It's just to state how extensively this technology is being tested for accuracy. Here, they tested it out with basic GoPro cameras for this study and still managed to get high resolution models. And the best part, it's very cost effective in terms of the field time requirement and the quality of output that we get from it. This is my favorite part. I always say it's not just 3D, it's 4D, because it has the capabilities not just to give you information about the X, Y, and the Z axis, but also time, which is like the fourth dimension added to it. So here what you see is Lewis took some photographs of endemic endangered Mediterranean coral called Cladocora cespitosa. In 2023, he surveyed the colony, and in 2024, he tried to survey the same colony, and we tried to see the change over the years using photogrammetry. If you see here, the green signifies no difference, and the red shows degradation, and you see a gray spot here. So the gray is where the software is not finding common points between these two models from 2023 and 2024. And now if you come back and look at it, you see that a whole big coral colony is lost. This could have been because of physical damage, because of anchor or a storm, or because of a corallivore fish. Could have been anything, we couldn't say. But the key takeaway is this output or this visualization has such an impact, especially for policy making. It's important for visualizing the change over time, for making impactful decisions. In a similar instance, we tried it on another one of our projects. So in a month's time, if you see here, you can see a small tunicate would be a couple of centimeters in size. And the algorithm is able to estimate it and see the change in a very high precision. So the tool is also very versatile. I want you guys to focus on the first part of it initially. So apart from the ecological parameters, you also can derive topographic parameters from the photogrammetry output. So what are these topographic features? You can estimate the complexity of a reef. You can estimate the slope of a reef or an aspect, what we call. You can estimate fractal dimension and other topographic matrices, which are often linked to ecological parameters like abundance, diversity, species richness, cover, etc. So using different photogrammetric outputs, you could derive topographic details, you could derive ecological details, and then you can find the correlation between two. It's not just used in marine ecology. Let's take an example for archaeology. I think it's archaeology's favorite tool to use because it's creating a permanent digital record of the past. You can create an archive of a shipwreck or an ancient remain or ruin of a town, and you could have it hosted online and revisit it with high accuracy. And you could also then take these outputs into game engines and visualize them in what it could have been in the past. Coming to another application, critical infrastructure monitoring. So here, if you see, this is highly, I'd say, more expensive kind of projects where on the right side here, you see a dam and the markings are of a marker used to scale these models to have high accuracy. These projects were always taken with ROVs, and here you can see a working class ROV. So these are high budget projects. It's also because these are deep sea critical infrastructures that could be monitored with, or rather inspected with high precision, because a lot of importance for the internet cables and other infrastructure going down, it's worth a lot of money. So you have to invest in a lot of money to inspect this, to know if there's any damage or if it's an oil or a gas platform, if there's going to be a potential leak, things like that. Now you'll be wondering, how do we get to this stage? So what are the data formats like, for example? Starting off, so I split this table or the slide into two parts, the 3D part of it and the 2D outputs or data outputs of photogrammetry. The first one is a point cloud. Imagine you have hundreds of images which is organized in a three-dimensional space using millions of common points that are identified from these images that you collected. So you have a base, you have a lot of points scattered in a three-dimensional point. This is further processed into what we call mesh when these points are collected. And this mesh can then be transformed into what we call textured mesh because we have the detail about the texture from the images that we collect. If you remember the coral slide that I showed you, we use point cloud to compare the change. But if you were to calculate the surface area or volume of something, you'd use a mesh here. Or a textured mesh, whichever you prefer, you could use for calculation of volume or calculation of surface area. And if you wanted to calculate change in volume, you'd again use a textured mesh. Now coming to the 2D part. The first thing would be a digital elevation model. So as the name suggests, it gives you an output of the relative change in the elevation of the model or the subject that you're trying to make a photogrammetry model of. And the second is orthomosaic. This is also another favorite of mine. Now imagine, I forgot to add a scale to this, but this is a site of maybe 200 meters in length or 150 meters in length or more. So we've used almost 8,000 images in here. And this is a result of 8,000 images binded together into a high resolution image. This image has details like you see here, like it has the capability to give you high resolution details like holoturin you see here, Posidonia meadow or a sponge. So you can estimate the species diversity or abundances of species cover using this part of the photogrammetry output. Taking it a step further, just to give you an overview, everything starts with the image collection. If your image collection goes wrong, you can kind of imagine that the rest of it falls apart. The most important part of this methodology would be the image collection. Depending on if you have like a survey area above the water, you could use a drone. Or if it's underwater, you could have a diver with camera or an ROV or an AUV, depending on your project needs. So how do you collect the data? How do you collect the image? The image collection is very important and it needs an overlap of 60 to 80% for it to work well. What do I mean by this overlap of 60 to 80%? So if you see the image in here, this is two different images, but you see that there are a lot. I just highlighted two common points to show you that in this part of the image, we don't have this common area. In this part, we have this area more. On this image, you cannot see that it's having the same result. The basic idea of it. The adjacent image needs to have so many common points such that the software can stitch them together. That's the basic idea behind it. And depending on what you want to make the 3D model of, maybe it's a colony. So you could use this pattern of just spiraling around Gorgonia, for example, or a sponge or a coral. But if you want to do it at a larger scale, what you do is you make something what we call as a lawnmower pattern across the habitat scale. Or you could also go in a spiral way where in the center you have a determined pole, a predetermined position, and you have a tape that lets you go around and round and round of the desired area or diameter you want to make a 3D model of. But so far, the software still doesn't know what 1 meter would be like. We haven't given the software an information about the scale. That's when what we call as ground control points come into picture. So the two ways to scale your model to high accuracy is either using a stereoscopic rig like this, where you know the distance between the two cameras, or using something what we call as ground control points, because you know the distance between these 2 points or these 2 points, and you just lay it on the field. And later when you come, you tell the software, or you input it in the software, that this distance is 10 centimeters, for example. So the photogrammetry software scales your model accordingly. You don't have to use a fancy rig like this. I'll show you a few examples where we have created very high resolution model using basic action cameras. Going to the next, the softwares. Now you'd ask me, what software should we use? These are just a list of softwares that I am aware of. And okay, I've not used all of the softwares, but the ones that I commonly use is what we call Agisoft Metashape. It's not a free software, unfortunately. It has an one-time subscription. For the student subscription, I think it's 140 euros. For an institutional license or a private company license, it's a bit more. The other two options that I've tried and tested is Reality Scan and 3D Zephyrus. Both of them work really well. Reality Scan was earlier known capturing reality or something. This is a free tool to use, Reality Scan for sure, and even 3D Zephyrus, I think, where if you're not earning an income of €1 million or above, don't quote me on this, but it has a clause like that. If you're not generating revenue out of it, and if it's for personal or small scale purposes, Reality Scan is free to use. Unfortunately, I have not used any of the open source processing to get the mesh or point cloud or any of the processing data set. However, I've only used open source data to analyze these outputs. For example, Cloud Compare in here. If you remember the coral comparison, we analyzed it on Cloud Compare using the point clouds, where Cloud Compare lets you compute the distance between the two corals. For computing surface area or volume, you could use what we call MeshLab. And for other topographic indices that we use, you could use QGIS. And another part of it would be for communication and outreach. I think it's very important because most of the time scientists forget that we did such an amazing job, but how do we communicate it to the citizen? So in CMMI, we have one of these projects where it's a project by the Tourism Ministry of Cyprus, where we create, by the end of the year, 43 models from important dive sites around Cyprus, which are going to be hosted in a platform called Sketchfab for anyone interested to interact and visit the site and have a look at the dive site before they go diving. And this is one of the videos that I wanted to show of how we do it for this project. If you see here, we have a custom built rig where there are 5 GoPros attached, and we could get this high resolution models out of it. Some of these models are also not just GoPros. We've used another digital camera, which is with torches, which gives you a much higher resolution. You can imagine a GoPro's image output would be like 3 MB, but if you use a much higher quality camera, which could have more image information and gives a data output of 12 megabytes, you can imagine the quality difference. But you have to choose what is more important for you. Like, is it the texture quality or the measurements that's important for your project purposes? And the scale for this project, the scale was like 200 meters square or around that. All of this was taken by Louis, by the way, I think. Okay, and moving on. So we decided to take this a step further. We tried to use something called as augmented reality to make use better and give an extended life to our models. We have been getting so many positive feedbacks on this. It's one of the, how do you say, it gives you that peak curiosity with people. People are always curious to see, it's giving a shipwreck out of the cart, and everyone's always wondering how you do it, and could we have one? And in our conferences and the public events that we did, it's been a massive success. So we decided to take it another step further with virtual reality. So if you see in here, we have this Gaussian splat model of the shipwreck that we did last year, and kids absolutely love this. It gives you a chance to get to the people and explain them what we are doing, what our work looks like, and sensitizing and making awareness workshop of why it is important to protect what we have around us. And lastly, like any technological advancement, there are some constraints that come with it, or limitations rather. First of all would be the environmental constraints. If it's a bad visibility or if it's a bad weather conditions, you'd have to plan your dives or your data collections accordingly. It's important to have a good image overlap and quality. What I mean by quality in here is if your data is blurry or overexposed, it's highly likely the software is going to struggle and not give you a good model. And as I mentioned earlier, structure from motion photogrammetry especially is a bit, it is a bit, how do you say, it struggles a bit with reflective or transparent surfaces. So if your project involves reflective or transparent surfaces, you'd have to give it a better thought, because it has happened to us so many times that we have been in a very shallow dive sets where it's 2 meters and we do an hour survey, and when we run the models, it's a lot of reflections and glares from the sun, and the model doesn't turn out good. So lastly, the computational demands. You can imagine if it's a large project with thousands of images. For example, we had a project with 60,000 images. It's computationally challenging depending on the scale of your project and the storage. Each of these project files have a bigger storage requirement and backup requirements. So you have to plan accordingly depending on your project needs. And that's the references. And I think we will take the Q&A, but in the meantime, while we have the Q&A, if you have your phones next to you, there's a QR code which you can scan to see the AR models that we have. And once you scan it, your phones will prompt you to show the picture of the shipwreck. And once you show the phone the shipwreck, it should project a shipwreck for you. I think we're open for questions in the meantime.
Nikhil, while the participants are scanning and trying to look at the very cool wreck, I must say, I think it's important to acknowledge also the input by the University of Southampton on this this important project for us. Okay, I think that we can give it a minute if people want to think of any questions. Please don't be shy. Feel free to write in the chat your comments or questions, and perhaps now it's time to give the floor to Gil if he wants to say something.
Hi everybody. I found this talk fascinating. I hope everybody else felt the same. I have a little bit of experience with that. I had actually a master student who did exactly that with GoPros. We tried to link between the 3D structure of the reef, or the seascape of the reef, and the fish communities, and different complexities and topologies. It was a very kind of preliminary work. It showed a lot of promise, but it also taught us all the limitations that you mentioned in terms of if you work in very shallow waters and so on, and reflectivity, how many of the photos you can use and so on, and the need for a lot of replication. But I think it has a brilliant future, this kind of work, and for ecology of risks, which we're trying to do in PUREEF-Y. I think the cool thing about it is that you don't need even, as you said, fancy equipment, but you need to know how to do this for sure. So if there's any questions on the floor or in the chat, rather, please go ahead and post them, and I will try to read them and see if the team here can come up with answers. So we have Shai Zilberman from my lab, actually, who's asking about how the plurality of cameras assist you in creating good model. In other words, what the 5 GoPros on a stick gives you compared to, for example, 2.
Good question. So it's just since for our project, especially for this project, we wanted to cover a larger scale of area. So what the 5 GoPros does is it lets you swim less. We're doing it by swimming. So if you have 2 GoPros, you'd swim a lot more to cover the same amount of area, which you'd have if you had a bigger stick with 5 GoPros, for example. So just that's the basic reason, to cover a larger area in the least amount of time.
By the way, when we did it only with 1 camera. You can do it also with 1 camera as long as you have enough overlap.
Yes, but
so what is the advantage of 2/1?
So when you use 1 camera, the thing is, there is no scaling feature. So when you're using 1 camera, you need to have reference points in your reef so that you can scale the model later in your software. Right. If not, the software doesn't know what 1 meter is, what 100 meter is. But when you have a stereoscopic setup where you know the distance between the 2 cameras, you know, you can tell the software, okay, the distance between the 2 cameras is, or rather 2 sensors is 10 centimeter. So the software scales it accordingly. Right. And then you can
remember that we had to use targets with the scales to do that. Okay, cool.
Exactly.
Here's another question from Sri, who asks, do you use specific lights like red or to get images with a higher resolution?
Cypress fortunately has really good visibility. So at the moment, for the models that we use, for the reef scale, we haven't used any lights. For the corals, we used video lights or strobes at times. But in general, I don't think we have used any red filters or anything to color correct it. But I'm aware that there are software that lets you color correct post your image collection. So you can bring your pictures back to the office and then color correct it and then process the models. So just an additional step.
There's also actually one of our colleagues at the University of Haifa developed all sorts of really cool tools to remove the water from the images by putting a color scale underwater. So there's this. I think if these 2 techniques combine, you can get really live colors even at 15-20 meters. But how about really going when you go deep with an ROV, for example, to where it's the light is dim? I guess you need very strong strobes and stuff to get a clear image, no?
Yes, when you go deeper where the light is barely visible, you need good strobes or lights, video lights, to take the pictures. And you have to keep in mind to not have the images overexposed, because if it's overexposed, the model wouldn't run well. If it's underexposed, it wouldn't run well either. So you have to know what the right setting is to have a good model in deep sea environment, for example.
Great. We have 2 more questions here, and I have a few of my own later on if people don't volunteer to ask more. So Dolfo asks about on the organism scale, for example, is Cystosera, what would you recommend given the complexity of this macroalgae? Which leads to one of my questions. When you have a mobile, something that like algae that actually moves with the current, how does the model capture that? Because I know that people have tried to estimate change in biomass also of seagrass or whatnot, things that are moving over seasons by comparing different models and so on. So how do you first deal with such high complexity, and how do you deal also with a thing that moves?
Correct. So I have a slide in here, and exactly this one. So as you said, if something moves, it's hard to find the common points. So if it's Cystosera or Posidonia, things or other macroalgal species that you want to estimate morphometrics of, it is a bit tricky. But what this study did here was they had also a multi-beam survey done where they combined both the structure from motion data and the multi-beam data, overlapped it to track these changes. And then they also use machine learning models to segment it and track the rate of change. It was a restoration project that they used it for. So
there
it is
are
possible.
ways to overcome the movement of your seascape.
So sorry, Gil. I think I lost
so
you
there
there.
are ways to overcome the
Yes.
The fact
In a
that
way, yes.
Your seascape is sometimes moving.
In a way, I think in a way, yes, there are ways to do it, but it's another set of investment. For example, if you had to do a bathymetric survey here, like they did it for this study, it's another investment of time and the equipment to map it accordingly. So depending on the resolution or the detail that you need, it is definitely possible.
Okay, cool. Here, and Alba is asking, she's saying, I used the structure from motion during my research, and I found very difficult to create a qualitative model of reef starfish, I don't know what, because of the three-dimensionality of the coral cages. I don't know what coral cages means here. Glint, change of light condition, etc., and 2-3 meters from the surface. She tried GoPro on camera, taking shots manually. Do you have any recommendation in this particular condition? I know she's asking also whether it's better to use videos or manual photography. But if you see the question in front of you,
do I have it in the chat? Let me see.
It's in the
But
chat.
from what I understand, we use time lapse. So there are features on GoPros and most of the modern cameras where you can take images at set interval of time instead of taking videos. It's a preferable method because the images have metadata that lets the software do the calibration step easily for creating the 3D model. But in this case, since it was very shallow, I'm assuming the models didn't turn out well because of the glare or reflections in the water. If it's like 2-3 meters, it's highly likely. So maybe in a day with overcast, it would be a potentially successful survey. Also depends
So you
how.
recommend working in shallow waters actually when it's overcast, when there's less light and also less reflection.
Exactly.
Cool. Thank you. So Iris, also from my lab, a PhD student in my lab, asking, how do you make sure that the overlap is sufficient?
Oof, good question again. I think it depends if a diver is surveying it and if it's a large scale, for example, let's say 10 or 20 by 20 meters of area, the surveyor, the diver needs to have a good estimate of the positioning of the diver himself to know that, okay, he covered this area, so I did this zigzag pattern and I covered through making sure there are no holes in the model. Luis has something to say.
Just a comment from my side, because I've been collecting data for photogrammetry for some time now, and I would say it's based on experience.
Yeah.
Especially the first few times we overdid it. We collected many more images than we actually required. Until we got the hang of it and we thought, okay, maybe I don't need to spend so much time taking images with more overlap that is actually needed to save time, basically, because if you have the opportunity to collect more images, then you might as well do it. But sometimes, depending on the challenges of the dive or the object, you don't want to spend too much time. So I would say that you need to try it a few times and do more in the first few times, and then you get the hang of it.
It also depends on the speed of your diving. You don't want to go too fast because then you don't have enough overlap, right?
Yeah.
Of course.
But also not too slow because you cannot cover. There's all these little details, I guess, that comes with experience and talking to people who has experience, right? Okay, move on to Muhammad is asking. We said he works on site depth between 10 and 30 meters, right? I guess not centimeters. Depth with the, or maybe centimeters. He can tell us. Depth with a 50 by 20 meter length and width. Not that deep. The sun caused a caustic light, maybe chaotic light, and this effect on extractions of the key points, then the type points. Do you have ideas that can help photogrammetry work in that conditions, in these conditions?
I think he's working in one of the most difficult environments, I'd say. When it's that shallow with that amount of reflections and diffractions, it gets a bit more trickier. If it's possible, if it's an intertidal area where the water goes down completely, maybe he could try to survey it when the tide resides. I know there is something called as fluid lensing, which is used for UAV related surveys, but I'm not an expert. I've not done it by myself. I'm not sure.
I mean, to do intertidal, you actually have to be out of the water.
Yeah.
To do this.
Yes.
And unless he meant 10 to 30 meters, I'm not sure. Anyway, Andreas from CMMI is asking, can it be done in real time on the edge? Well, I'm not sure what he means. What do you mean real time? But maybe you understand this question.
If actually there in the very recent times there are some algorithms. I think it's called SLAM that lets you create point clouds that we earlier spoke about in real time. So there is a way that in real time you can see what you're surveying, but it's usually used for ROVs and technologies like that. We've never seen like a diver use this, but it is possible. Like there are stereo cameras that uses SLAM algorithm. I think Andreas works on computer vision. He would probably be aware of this algorithm called SLAM that renders real-time 3D point clouds. And later you can
real
bring
time
this
meaning like in your cam.
What do you mean? It's a specialized set of software and camera. I don't know if I have it somewhere here.
So you come back to the lab and you already have a model.
In a way, I think it's called SLAM X2. Are you able to see the screen that I'm sharing now?
Yeah.
So this is one of the technologies that's currently in the market that lets you have it somewhere here, I think. Give me a second. It's here. If I move this, yeah. So this lets you render things in almost real time. It doesn't create a mesh, I think, but it lets you see what you're scanning out of your survey so that you make sure that there are no holes in your model. So in a short way to answer, I think definitely it is possible.
Cool. Okay, we have 6 minutes more, so let's move on. Luigi is thanking you for the presentation and asks, do you think that merging machine learning algorithm and photogrammetry techniques can be used to classify coral species and detect early signs of bleaching or disease in shallow reef habitats over long periods of time?
Another good question. I have a slide exactly for that too. So there is already a software called TagLab that lets you do this. So they have a segmentation model that helps you. Once you have the 3D model, you have to export it as a digital elevation model and orthomosaic. And then using TagLab, it's an open source software, by the way, you can estimate these metrics that he said. He classify coral species. It is possible. Detecting early sign of bleaching, this I'm not sure, but you can estimate the coverage pre-bleaching and post-bleaching, or does it, yeah, I think this should cover the question.
Yeah. So combining AI with this
Yes.
can really enhance your data that you can get from. Alba is asking again about reef star. She's explaining what reef stars are. These are metal cages used to transplant corals. Okay, now we understand better the question. And also ask again, how do we capture the fine scale details of complex organism structure?
It depends on the cameras you use and the number of images you take, because in the end of the day, like, do I have it here? Here, if you see, this image was taken using a high resolution camera and not a GoPro. So the model output of it was, even the geometry of it was immensely high quality. So if you use a good camera setup, it's easier to achieve it.
Mm-hmm. I guess if you really want to follow individuals, you would have to come closer. So you cannot catch everything, both very, very high resolution and very large scale, but you can find some middle grounds, I guess, depending how accurate you want your things to be.
It depends on the balance you want. There are some scientists in Australia who have two cameras set up, where one of the cameras is like zoomed in with high resolution photos and one is more of a wide angle. So in the same habitat scale model, you have very high resolution colonies captured as well. So if the budget allows, if the computational capacity you have, it's definitely possible.
Alba is asking again, or commenting again, that cloud compare software is more useful to detect what remains equal between the clouds. What is the missing from one cloud to another, or both? It's a question.
Compare. Let me try to read the question again. Cloud compares. Okay, so I think I can answer this one. So when you have the same set of, again, it depends on the overlap and the common points. If you have two models where there is nothing common, Cloud Compare wouldn't be able to give you a good result. But a good amount of overlap could result in, let me show the model here. So if you see here, we had a lot of space that was very common. If you look at this point in here, it was common. So it's detected in here. While the ones that the software couldn't find, it grayed it out saying that, okay, I couldn't find it, so I don't think it's there in this model. So it has the capability to give you a visualization of both.
Okay. There's a couple more questions. I'm going to ask a quick one myself. So imagine that you do the 3D model. Now you want to put fish on this model that you counted. How do you envision we can, because we want to relate, for example, the fish distribution to the habitat, and we want to put fish on the map. How do you envision we can do that? It's something I'm really interested in doing. We tried a little bit to do this, you need to first create this map and then go and, how to put the fish in a 3D space that can also be linked then to the habitat. Do you have any ideas about that?
I know there is a couple of studies that link the abundance of different species of fish compared to the structural complexity. So what they do is they do a separate fish surveys, and then they do a separate photogrammetric model, and they statistically try to see if there's a relationship between various topographic features like rugosity, structural complexity, fractal dimension, roughness, to this abundance of fish species. I don't know if
but
that
this is
answered
at
the question.
this is at the whole model scale. But I wonder if on this model you can put fish, the location of fish, and relate them to specific features within this. That's kind of the next step, which is not trivial at all. Yeah.
I'm not very sure if you can do. I'm not sure about it, Gil.
Yeah. I can go on and on, but let Miriam has a question. Had taken photos of the coralligenous habitat on the seafloor using a 50 centimeter quadrat over an area of 5 by 5 meters. However, when I tried to process and align the images using Agisoft Metashape, it didn't work as expected. The alignment did not reflect the actual arrangement of the photos I have taken. Is it due to the methods I use, or is it another reason for this issue? Is there another reason for this issue?
Without looking at the pictures, I'm not sure. I never had this problem myself yet. Unless there is not enough overlap, I think it should give you some result. If I can have a look at the data, maybe I'm able to say what could be the possible reason. Without looking at it, it's a bit tricky to say. I think Louis has raised his hand.
Thank you so much. Yes, Louis, you have a comment, question?
No, I was just going to say that we are right on time with the last question, so it's perfect. And I put a message in the chat that if any of you have any more questions, don't hesitate to send an email to Nikhil or to myself, even though Nikhil will be probably the one answering any more technical questions. I think it's time to wrap up. It's been a really nice webinar, I think. We've had lots of questions, interesting questions, important questions. It's time to wrap up. As you have understood, it's a topic that is of high interest to many different disciplines. And it's very dynamic. It's changing constantly. New technology is being added, and I think that in very few years, or it will be the norm to be using photogrammetry for any kind of underwater or even terrestrial research. So thank you all for attending. I would like to ask you to register for the PUREEF-Y newsletter and also follow us in the social media channels. And I'm happy to say that you should expect more webinars in the future from our side under the framework of PUREEF-Y. And I hope to see you and more in the future. Thank you, Gil, very much for moderating. Thank you, Nikhil, for a great presentation and inspiring discussion. Thank you, everyone.
Thank you.
Thank you, everyone. See you.